So, good morning students. So, I welcome you in the lecture series of electronics devices circuit. This subject is very important as far as your knowledge is concerned and as far as any competitive exam is concerned. So, till that what we are seeing in this particular lecture, what we are doing is nothing but the DC biasing of BJT. Sorry, just a minute. I will take pen first. Yeah. So, we are discussing about the DC biasing of BJT. DC biasing of BJT we are discussing. So, for this I have taken the previous lecture. In this one I have explained the thing to that what exactly mean by biasing technique, what exactly mean by biasing and what is the need of biasing to you. If you have not watched the videos, please go through the playlist and you can watch the video of the previous lecture in which I have explained the things regarding the biasing, what exactly biasing or need of biasing. So if you are not subscribed my channel, please subscribe the channel, click on the subscribe button, you can subscribe the channel and you can watch the entire video by browsing the playlist of electronic devices circuit, and you can enhance your concept and you can clear your concept in the detailed manner. Okay, so you can watch the entire video series of electronic devices circuit in the detail. Okay, so what exactly mean by biasing, that I will explain to you. That biasing nothing but we have to give some DC voltage to the transistor, DC voltage to the transistor there, so that the transistor can amplify the signal. That is nothing but we have, again I will explain thing to you that suppose this is the amplifier I will denote by A, and this is the input given to it and this is the output taken from this one. So amplifier is anything is nothing but suppose if I am talking with you guys and my frequency is like this one, okay, my input signal, but if same speech I have to convey this to the auditorium of 400 and 500 students, so this should be like this one, its amplitude must be increasing, frequency remains same, amplitude must be increasing. So to amplify this I require a thing that is called as amplifier. Okay, so input is AC and output is also AC for this one. but the thing is that we have to turn on this device by applying some kind of voltage, that is nothing but a DC voltage. We have to apply a DC voltage for this one. So we are using a transformer, then we are converting into rectifier, we are converting into DC. By this one we are applying to the amplifier this thing. Okay, so this is all about the DC biasing. So apply a DC external supply to the amplifier wherein transistor is called as the biasing. So we have seen this thing. So there are 5 types of DC biasing, that are nothing but the fixed bias, emitter stabilized bias, collector emitter loop, the voltage divider bias, and DC bias with voltage feedback. So I have already told you that this biasing technique, voltage divider bias, is important thing, and we have to learn the each and every technique because it is having its own significance to each and every technique, which are having each and every technique is having its own significance. To know what exactly mean by this fixed bias, this emitter stabilized bias, the collector emitter loop, voltage divider bias, DC bias with what you can say voltage feedback, that's all the things are there we have to learn in the detail. So I have started with the DC biasing, that is nothing but the first technique is nothing but my fixed bias technique. So what exactly means by fixed bias? So I will take a transistor over there, connected one resistor, that is nothing but my RC. So and I have connected one resistor, that is nothing but RB, that is connected to the base terminal of the transistor, and this RC is connected to the collector terminal of the transistor. So emitter is directly connected to ground, and these two things I have connected simultaneously and connected to the VCC, that is nothing, this VCC is nothing but my DC supply, and here I have applied one capacitor and here I have connected one capacitor over there. Okay, so role of the capacitors I will explain in the detail afterwards. So this is all about this circuit diagram of this one. So as far as this resistor is concerned, if resistor is there and the supply voltage is there, so current is caused to flow. So the current caused to flow from the base is nothing but my IB, and current caused to flow from the collector is nothing but my IC over there. Okay, current caused to flow the IC, and the drop in between these two terminals is nothing but my VC. So I will tell you the things to you. Suppose it is written as VCE. Okay, so how to read this thing? So this V stand for voltage exactly. Okay, and this capital stand for DC. Keep in mind, capital is there, so DC voltages. Like this one, suppose small VCE is there, VC and C, and this small E is there. The small is there, that will represent the AC signal. Okay, AC voltages itself. So yeah, so suppose VCE is there, so what it means? What it means? Why have it is not written as VCE, VEC? Sorry, VEC. So difference in between these two is that. Suppose VCE is written over there, VCE is written over there. That means the voltage, it's okay. V about voltage. So C is more positive than this emitter. That is nothing but the collector is more positive in the sense that is connected to the what you can say, high potential. I will denote as high potential. So this C I have connected, this C is connected via resistor to the VCC, and the E is connected to the ground. So that is VC is more positively than the E, that's why VC is over there. And if I am writing VCE, VEC, that means I can write over here, because E is connected to ground and the C is connected to the VCC. So VCC is more than my ground voltage over there. So that's why I can write VCE only, not VEC. If I am writing VCC is equal to minus 12 volt. So then case I have to write a VEC. Why is it so? Because V is having 0 potential and C is having minus potential. So greater potential is CE over here and C is connected to the minus supply. So that is correct one. Are you getting the things what I am doing? If you are getting the thing, give me thumbs up in the chat box so that I can understand that you are getting the things. So this is the significance of this one. So we have to, from this, why we are calculating this? Because we have to calculate the value of as far as this graph is concerned. This graph is concerned, I must know the value of IC and I must know the value of VCE from this. I am having just this circuit diagram and I don't know what kind of current is going to flow, that is IC over there, and what is the value of VCE over there. Because if these values are less one in the sense, if this value, suppose this value is very less, so at the C point it's near about 4 point something milliampere, and this is not about 4 something, okay, 4 volt. Suppose I got the value of VCE is 4 volt and this is IC is 4 milliampere. So this is shown by this A point. So this is near about the saturation region, near about the cutoff region over there, near about the cutoff region. So what will happen in the, if we know that if my device is in the cutoff region, near a cutoff region, it will act as a open switch. The current will not close, current will not flow. So to operate my device in the amplifier, so the current should be in the mid of, keep in mind, mid of, what you can say, mid of my linear region, that is nothing but the center. It should be at the center of DC load line. That is the correct thing. At the center of, not over here, maximum. It should be at the center. So why is it so? Because it will amplify the signal properly. That's why we required my Q point should be at the center. Yeah. So apply a KVL if I am thinking about the input. So this is a structure that we have to draw. So input, apply a KVL. So what will happen? Minus to plus, I have to write plus VCC. Then plus to minus, I will write drop. I have to calculate. Okay, drop. So this is nothing but my VB drop over here. Okay, and the VB is denoted by RB into IB over there. That is nothing but minus IB, because plus to minus, higher potential, lower potential, we are denoting by negative. Then VB, why we are, because minus plus to minus we are going, so minus VB. Keep in mind this VB, it's all about 0.7 volt. This value is fixed one, 0.7 volt. While solving the problem, we will see what is the value of VB. VB is 0.7 volt, because if silicon diode is concerned, this transistor will turn on at 0.7 volt over here. Okay, for solving for IB, because if I am solving for IB, then I will get the value of IC. So from this IB is equal to what? I will shift this IB to this side. So this will become plus, and VCC minus VB divided by RB is nothing but my IB over there. From this first I got this thing. From collector current, that is IC is equal to beta time IB. I know that this formula IC to beta time IB. So beta is nothing but my amplification factor. This value is near about 100, 190 or anything. The value is depending on the manufacturer. Okay, so beta times of IB. So eventually what will happen? IB is less one, so beta is multiplied with IB and we are getting the magnified amplified version of IC over there. And if I am applying a KVL at output side, then what will happen? Minus to plus, that is nothing but the VCC I will get, minus ICRC, and minus here VCE. From this I will calculate the V is equal to 0. From this I will calculate the value of VCE. From this we will calculate the VD. So VC I will send to this side. So I will get the equation that is nothing but this one. So VC is equal to VCC minus ICRC. We are getting one. Okay. So though, and the isosaturation maximum current is nothing but what? VCC divided by RC. That is nothing but my VC is equal to 0. That is nothing but here. If you are observing the graph. Here, what is the value of isosaturation? IC. What is the maximum value of IC? That is nothing but IC is equal to VCC divided by RC. Forget about this graph. This potential. This potential it should be 0. That is nothing but. Why is it so 0? Why is it 0? Because if in the saturation region, transistor will act as a transistor. Both junctions are in the forward bias. So forward bias is nothing but this is act as a conductor. So this will conduct, and if it is conduct, so its voltage is 0 over there. This voltage is 0 over there, and what will happen in this case? Voltage will be 0. Then what will happen? Whatever the IC is nothing but VCC divided by RC. That is we have inverter like this one. So load line analysis that we have to see. This is the very important part. Yeah. Okay. 3 to 4 slides are there. So what exactly mean by load line analysis? That we have to see first. First of all, we know that what is the maximum value of IC from this? That is nothing but VCC divided by RC over there. Okay. So this is the maximum value of IC. This is maximum value of IC. That is nothing but VCC divided by RC over there. Okay. Then VC is nothing but what? VC is nothing but what here? If I am writing VC, just a minute. What is value of VC? VC is nothing but all about the voltage that is taken by this RC, and the remaining voltage is nothing but my VC. I will simplify this thing to you and clearly. Yeah. Suppose 15 volt is given to you. Okay. So if this resistor will take 10 volt, so remaining voltage is taken by this transistor. That is nothing but how much? 5 volt is remaining, because we know that input and output voltage, that is the, we know that KVL is there. KVL, if I am applying KVL, the input and output are the same one at this point. Suppose it's KCL. Okay. So current I, if incoming current is equal to outgoing current, so I like with this one, same will happen. Whatever the 15 voltage is taken given by the battery, then some voltage is taken by this one and some more voltage is taken by this one. So if this is taken as 10 volts, so remaining 5 volt is taken by this transistor, this VC voltage. So what is the maximum value of this VC? What I exactly mean by maximum value? Suppose nothing is taken by this transistor, so nothing will is nothing but what? If my IC is 0, my IC is 0, V is equal to IR, I am saying IR. So I0, that is nothing but the product of this is 0. So you will get voltage is equal to 0. So that is what is this? VC is entirely VCC. So I have taken this 2 point and I have drawn the graph. I have drawn the line over there. Because I need a maximum value of VC and maximum IC and maximum value of VC. So these are the two, and I have taken these 2 points. Okay, and this line is called as what? Load line. Maximum value of IC and maximum value of VC. Take this and join this graph, and that is nothing but the load line. And the Q point is nothing but the point over here, anyone on this line any point on this line, but it should be at the center. I will tell you the significance of center. Why is it not at the saturation? Why is it not at the cutoff region? Okay, so exactly. Just a minute. I will drop the portion first. Okay, just a minute. Erase. Nothing is to erase over there. Okay, so what is this graph shows to you? What the graph is showing to you? So we are having different value of VCEC. Just a minute. Yeah. So first of all, take this one. Suppose I am taking the value of VCC is equal to 15 volt, and my R is near about, I will take 1 volt, 1 ohm I will add. Okay. For calculation purpose I am taking this thing. So this is nothing but my 15 volt over there. Okay. So that is nothing but the current is 15. So this current is very more. Suppose second case, VCC is less one, that is nothing but I will take as 10 volt, and the resistance is same one, that is 1. So I will get the current is 10. So this is the more current, this is less current. Again, if I am decreasing the voltage, so this point will decreasing, and this line will shifting from this end to this end, from this end to this end, from this end to this. So the line is totally depend upon what VCC is in the first case. Okay, and if I am talking about the Q point, it will again shifted to this side, because the Q point is on this line only, The Q is nothing but the quiescent point. We will discuss about this thing. In this case, VCC1 is greater than VCC2 and VCC3. Okay. Now, first case we have taken the different value of VCC. Second case, what we will do? We will take the value of R different. That is nothing but we will take 15 as it is voltage, and R we will take first case 1, or first case 1, then second case 2, and third case 3. So in this case current will be 50, in this case current will be 7.5, and in this case current will be 5. Okay. So here you will get a maximum current, here you will get moderate current, here you will get a less current. So like this one, maximum value of R will give you what it will give you? Maximum value of R, this is the maximum value of R. Okay, maximum value of R. So maximum value of R give you less current, so this is less current over there, but VCC is fixed one, that is 15 volt. Again, if you are increasing the or we are decreasing the value of R, because it is inversely proportional. If you are decreasing the value, so current will goes on increasing, then Q point will shift it to again this side. Okay. So there is a significance of VCC and R over there. That is nothing but totally depend on this. VCC is always fixed. We are not changing, but we can change the R value, and totally this current is totally depend on the value of R only. So this case, what you can say, in this case what will happen, if my IB is going to be increasing, my Q point is also increasing, going to be increasing. Okay. So this is all about today's discussion of DC biasing. This if I am talking about the problem, if I am taking the problem, then your concept will be more and more clear. So thank you very much for attending this lecture. Thank you.